In this lecture, we are going to talk about ray tracing. The objective is to understand the structure of a generic ray tracer. We will also talk specifically about one component, namely ray generation and ray intersection computation. The chapter from Angel would be a good reference for additional information. So, what is ray tracing? The idea is to send a ray from the eye through the particular pixel on your image into the scene. The color at that pixel is determined by the intersection of the ray with the scene. Of course, light travels in the opposite direction in reality, namely from the light source, bouncing off the object, intersecting the image and the pixel, and then entering the eye. However, this particular way of looking at the rays help us generate the image corresponding to the ray. So here is an illustration of the eye and the ray emanating from the eye. The specific ray is determined by which pixel we are considering within the screen. This ray goes on into the view frustum and intersects different objects. Now, of course, the objects could be transparent and could have reflective properties. So what we would essentially need is a recursive form of ray tracing where new rays are generated after they intersect objects within the scene. These new rays are either reflected rays or refracted rays. This recursive ray tracing is able to simulate specular reflections and indirect illumination in addition to features like shadows. So, for example, the ray could go and hit A, reflect off to go and hit B, which in turn could reflect and go and hit C, which could reflect and go and hit D. And D is a refractive object, so the ray passes through the object and then eventually goes towards the light source. Of course, this is the path of the light ray in the reverse direction, and hence the algorithms or the method that's used for ray tracing is often called backward ray tracing. Now, ray tracing is able to generate interesting effects. So ray tracing is able to generate very high quality images such as this, where, for example, here you have a still life with objects that are highly refractive or reflective. Ray tracing also helps generate scenes like this, which is like a daylight scene with mildly specular objects, or a combination of both. So, what is the structure of a generic ray tracer? We assume that we are given the camera parameters, the camera location and so on, and the image resolution. The idea is to generate rays Rij, where the parameters specify the ray that goes from the eye towards the pixel Ij, in particular the center of the pixel Ij. We will talk about the structure of a function, let's call it trace R, which traces this ray into the scene. Trace R will return the intensity or the color at the particular pixel I, j. Right. So trace R applies on a ray R and follows it into the scene. Let's say O is the first object that it intersects and P is the point of intersection of the ray with this object. If O is reflective or translucent, then we would want to compute a reflected or a transmitted or a refracted ray and call trace recursively from the point P. So for each light source at the point of intersection, which is P, we would apply the Phong model to compute the shade if the light is visible from P. Now we would combine this shade together with the shade computed by the reflected and translucent rays to return the color at the particular pixel. So how do we compose or how do we compute this composite color, right? So the ray tracing equation for a single light source, it looks very similar to our Phong model. So the intensity I has a ambient component. It has a diffuse and specular component, which is suitably multiplied by the visibility between the point P, the point of intersection, and the light source. Of course, in addition, we have a recursive call. So Kr is the coefficient corresponding to the reflection, and we call trace recursively, remember. There is another recursive call to trace for the reflective or the transmitted component. So with this equation applied at every intersection point recursively, we will eventually be able to compute the intensity at the pixel. So next, let's look at individual rays and how they are generated. We used R to refer to a ray. Now, of course, a ray is parametrized by a single parameter t, which goes from 0 corresponding to the eye to infinity into the scene. The origin for the ray is, let's say, P, and we have a direction U. And in this case, the ray R of t is given by P, the point, plus Tu. In different implementations, choose to specify whether U needs to be a unit vector or not. How do we generate each ray? Well, we need the camera properties and the image properties. The camera properties is specified by the lookat function, which specifies the location of the camera and the direction that it is looking at. The camera properties also include the view frustum, which we know can be specified using the field of view, the angle of view, and for example the aspect ratio and the distance to the near plane. In addition, we would need the resolution of the image. Let's say this is an image with nx by nx columns and ny rows. So in this particular scenario, let's say that the ray intersects the image at a location ij. So we would need to write down the expression for Rij, and this can be written with respect to the eye. We know that in the camera coordinate system, the eye is origin, and we know the distance to the plane, so which is the near plane, we know the distance to the screen, we know ij from the specific pixel that we are looking at. We know the screen's resolution, the nx and ny. Together with, so using all these properties, we should be able to write Rij as a in this form, right? Where t is the parameter that specifies different points on the ray, and u is the vector that corresponds to the line shown here. It's this vector going from the eye through the pixel. So once we write down the expression of the ray, the next step is to compute the intersection of the ray with objects. Now, of course, there could be different types of objects in the scene. So the graphics primitives that we have focused on are planar. So it may be sufficient to talk about ray polygon and ray triangle intersections, which we know how to do. We know how to find the point of intersection between a ray and a plane, and more specifically a triangle. A ray sphere intersection is historically significant because some of the early ray tracers were written for objects that consisted of spheres, cones, and other conics. So this computation of this point of intersection is a simple exercise in geometry. Let's say that the point of intersection is specified by the parameter t. The solution could actually consist of multiple values of t. For example, a ray intersects a sphere at two locations. If an object is specified as a collection of triangles, then a ray could intersect that particular object at multiple triangles, so with multiple values of t. So of course we would choose the smallest value, t sub 0. Note that we want it to be greater than 0 so that the objects lying in front of the eye are the ones that are important. T0 or t sub 0 represents this intersection with the nearest object, which is our O, and the point of intersection is P. So one thing to note in conclusion is that this ray intersection computation requires the generation of the ray, which is easy, but more importantly, it requires that the entire scene is stored and is available in memory, because we need to check whether the ray intersect with all the objects in the scene. So this is one of the major bottlenecks of the ray tracing, especially the recursive ray tracing approach to scene generation. And this turned out to be one of the major bottlenecks and the reason why ray tracing was not so popular. However, with the introduction of a large number of cores in the GPU, these computations have also been parallelized now, and there are CUDA kernels available now to compute ray tracing in parallel. So with that, we will end our discussion on ray tracing, and in the next lecture we will see an immediate use of the actually a restricted version of this ray tracing for volume visualization.